Hello everyone, welcome back to the Calculus Fun Room. In the last video, we introduced the idea of calculating area under a curve. And again, as I mentioned in the last video, when I was discussing under the curve, it was, area between a function and the x-axis. So we thought about having a graph of some function and over some interval from A to B. What we were doing was finding the area under this curve. Now our approach was to initially estimate this area. So we split the interval into subintervals, and we use the idea that we were going to use rectangles. We wanted rectangles of equal width. So if we're using n rectangles, we would take the length of the interval, divide by n. That would tell us the width of each rectangle. So if I looked at the first rectangle, one approach was we used right endpoints, and we'd find the area of each rectangle. So a lot of times notationally, this first value in my interval we say is a, but we could denote that x sub 0, and then here's x sub 1 and x sub 2 and x sub 3, so on and so forth, and then the last number in our interval we would denote x sub n. So if we're using right endpoints again, then I would look at the next interval. There's my delta x. I would use the right endpoint to come up to the function. So what we did was we continued this process, and in the last video we had talked about using right endpoints, which is what I'm sketching here. We would talk about using left endpoints. We talked about using midpoints. Then we talked about the concept that in order to increase the accuracy of our estimation, what we would do is squeeze in, if you will, more and more rectangles. So we would let n go to infinity. And we had looked at a couple applets on the web. GeoGebra and Desmos both had applets to allow you to pick increasing values of n, increasing rectangles to calculate those areas. So what we had done at one point is we wrote out what we called the Riemann sum, and we had said the exact area was the limit, as n goes to infinity, of our sum of all the rectangles. So we had the function height for each rectangle and the delta x of each rectangle. So we're doing length times width, if you will, of a rectangle for all n rectangles, and we take a limit as n goes to infinity, and that would give us an exact area. Now again, we called this a Riemann sum, and that name Riemann sum comes from the mathematician Bernard Riemann. So he was the first person to introduce this concept of finding infinitely many rectangles, right, to produce the area under the curve. Now, as I mentioned in the prior video, finding areas under curves have lots of applications, and the application we looked at, the very first example in that video was we were finding distance. So we had an equation that gave us the velocity of some motion, and we were finding the distance. So when we found, area under the curve, that was giving us the total distance that we found. Now we will see lots of other applications in this chapter and future chapters. Really cool stuff. Some of them will be finding lengths of curves. The advantage to finding lengths of curves, if I think about, let's say, electric current flowing through a curved wire, we could calculate the total current. We could find volumes of materials. We can find centers of mass. We can find what we call hydrostatic pressure, which is pressure due to the force of water. We can calculate work done in moving an object. Lots and lots of different applications of finding areas under the curves. Now, if we look at this Riemann sum notation that we have here, notice that this is a summing process. It's really what this is doing, right? So we're summing up infinitely many values. And we will take a look a little bit deeper, right, again, at some of those applications. For now, what we're doing is we're focusing on this concept. At the end of this video, after we've focused on this kind of big picture concept, we are going to start to look at some shortcuts on how to calculate these things. And I want to draw an analogy real quick with what we've done in the past. When we first introduced the idea of a derivative, we talked about having some function. And again, we motivated this with, finding velocities. If this equation was a position, I could find the rate of change. So what we had done originally was found the average rate of change, right? And we called this a secant line. And what we had said was, if I look at f of x plus h minus f of x all over h, this gave me the slope of that secant line. So if here was x, if here was x plus h, I'm finding the change in the y values of x, f at x, and then x plus h, f at x plus h. So this was an average value. And then we found an instantaneous rate of change. Right? So in essence, we took this point here that I'm going to highlight in blue, and we let the h go to 0. So this point slid back to the other point, and we, in essence, created what we called a tangent line. Now, the beauty of the, and I don't want to do that anymore, right? We called this a derivative, right? And so this was an instantaneous rate of change. So the reason that I'm bringing this up is this limit process was crucial to us calculating what we called the derivative, the instantaneous rate of change of our function. And if we look back up at our Riemann sum, notice that we have the limit process involved there as well. So in the prior video, we used 4 rectangles to calculate, estimate the area under the curve. So in order to find an exact value, we're using this limit process. So as it turns out here, right, the limit process is a crucial tool to the 2 main branches or conversations of calculus. The first was differential calculus. We used that limit process to define the derivative here, right? And then next we're going to look at what we're going to call here integral calculus. So let's go ahead then and write the formal definition of what we call an integral. So I'm going to scroll back up and look at this picture real quick. In this picture I was using right endpoints. I could use left endpoints. I could use midpoints. In fact, I could use any point within each rectangle. And what I mean by that is represented in this picture here. So you notice in this first rectangle, if I look in this first rectangle here, we're picking, not even a point that's a left endpoint, right endpoint, or midpoint. We're picking what we denote as x sub 1 star. So we have the freedom to choose any representative x value in this first rectangle. Doesn't have to be left, right, or midpoint. Notice in the second rectangle, we did pick the midpoint. So for the second rectangle, x sub 2 star, the representative point was the midpoint. If I look in the third rectangle, I'm using something a little closer to the right endpoint, and that comes up to the function, and that determines the height of the rectangle. There's my dog barking at someone at the door. If I come over here and I look at the ith rectangle, is what we're going to call this, and I can use any representative point within that rectangle to come up, hit the function, and determine the height of that rectangle. So when we define the integral, we're actually going to use a more generic definition where we denote the x value we're plugging in to find the height, x sub I star. So again, in this formula that I wrote here, I was writing x sub I as the value that I'm plugging in. And that really represents the right endpoint. So if we're going to write a more general definition, what we're going to do is the following. We're going to look at the sum of, and I'm going to look at f of x sub I star. And again, that really represents that I can pick any value that I want within each subdivision, within each rectangle. So this value computes the exact area under the curve. And we're going to define this as what we call an integral. So we're going to look at the integral of f of x as x goes from a to b. Now this is the formal definition of an integral. And I could write down some things like 20 million sentences here to officially define it, but there's a couple things that we need to happen in this case. So f is defined in on my interval on a to b, where delta x equals b minus a over n, as we have discussed before. And as long as this limit exists, then this integral is defined. So I'm going to say when the limit exists. Now, in application, this limit's going to always exist. Now, what situations would this limit not exist? Well, what we would typically see in this class would be maybe a vertical asymptote. So let's say we're going from a to b, and we have a function that has a vertical asymptote, right? So we have what would seem to be possibly infinite area if we're interpreting this integral as area. Now, one thing that is allowable is a discontinuity that might be, what we call a jump discontinuity. So let's say we have a discontinuity that looks something like this. So technically, I could have measurable area here if you think about that, right? That would be finite area in that case. So the situations in this course where we're going to typically see that limit not exist is in a vertical asymptote. So that's a quick, rough sketch of the definition of an integral, and let's just talk about a couple things here in regards to notation and language and how we read this idea. So if I look at the integral from a to b of f of x dx, right, that's how we would read that, how I just stated that. So that elongated s, which really is a shorthand notation for summation, and that was a real sloppy integral I just wrote there. So this is called the integral symbol. And then the f of x would be what we call the integrand. So in other words, it doesn't have to be f of x, but whatever is sitting, I'm going to say, quote unquote, inside that integral, right? Whatever is sitting to the right of that integral would be what we would call the integrand. Now the dx is interesting, all right? So if we think about derivatives, I'm just going to remind ourselves, we started with delta y over delta x, and when we took a limit as delta x went to 0, this became dy dx. Now, in that limit process, the dx didn't really have any meaning to us. What we typically said there was that the dx indicated what our independent variable is. Now, we got lazy and we started to write this as y prime. We used Newton's notation. I don't want to say lazy, it's efficient, right? But the dy over dx represents we're taking the derivative of the y equation with respect to the x variable. So the dx in this integral is really kind of the same thing, right? It's indicating that this is the variable of integration, right? Now, of course, that really is, I'm going to say variable of integration, that really is representing the thickness of the rectangle, right? The width of the rectangle. So in a visual manner, that's what that represents, all right? But in regards to just looking at that integral symbol, the integral from a to b of f of x dx, the dx indicates this is our variable. Now, if we think back again, I keep referencing the idea of area. If we think back again that this is, we're interpreting area under the curve, this integral is always a numerical value. Right? So I'm going to say this equals a number. So it's measuring the area under the curve. It might be 5 or it might be 27 or whatever that number will be. Now what that means then is the following, that I could have any letters and variables in there, right? Just like we have done with functions up to this point. Everything doesn't have to be x as an independent variable. I mean, I have the integral of f of t dt. I could have a function of t. I could have a function of theta, g of theta d theta from a to b. And in fact, let me change the a and the b to, let's say, an alpha and a beta if theta was representing angle measures. So I just want to be a little bit careful here that the symbolism we're using doesn't have to be x's and f of x's. That's just kind of our standard way in which we write functions when we talk about generic definitions and theorems. So what I want to do here for the next couple of minutes is let's talk about some properties of integrals. Right? The first one being, I'm going to draw visually here. If we're interpreting this integral as being area under a curve, I've been drawing the function in quadrant 1 every time that we do this, but I mean I could have a function that doesn't exist only in quadrant 1. Now if I have a function like this, keep in mind if I draw rectangles, if I draw a rectangle down here in quadrant 4, when I plug this, say, right endpoint in, and I find that y value, that's going to be a negative y value. So it is extremely important for us to note that whenever the function exists below the x-axis, I'm going to have negative y values, and so my integral is going to produce a negative measurement there. Now of course area isn't negative, but because our rectangles, as I mentioned, have heights, distances to the function, those are going to be negative y's. Anytime my function is above, right, again if I were to draw a rectangle here, my y values are positive, and then I would have positive in that region as well. So anytime my function's above the x-axis, I'm going to get positive measure out of the integral. Anytime my function's below the x-axis, I'm going to get negative measure out of my integral. So some textbooks they'll come back and they'll kind of discuss this function f of x, the integral of f of x, and they'll say this is like net area. Net area between the function and the x-axis. So even though we initially motivated this conversation with area under the curve, we were calculating the distance traveled, that we drew all of those as positive functions, all right? But in a more general manner, we could definitely have the integral calculate positive or negative measurements. All right, there's some other properties of integrals we would typically see in a section like this. The first one would be that if I have the integral of a constant times a function, that is equal to a constant times the integral of the function. This is analogous to having a derivative where I have an integral of a constant times f of x. The derivative of a constant times f of x. I can pull that constant out of the differential operator, multiply it back on at the end. Now if we think for a moment, I just want to loosely justify what we're doing here. That in our definition, this is the sum of c times f of x sub I times delta x. I mean, technically there's a limit here, right? Now if I kind of expand that summation for a moment, right? Remember the summation is really c, and then I have f of x sub 1 delta x plus the constant times f of x sub 2 delta x plus dot dot dot. Now I still technically have this limit process that I'm carrying. But if we think about just factoring, right, each of these terms has a common factor of c. So I could pull the constant out and then just sum up all of those terms. So because I can factor out any common term within a summation, I can pull that c out, and then I have a property of limits that says the limit of a constant times a function is a constant times the limit of the function. Alright, so I'm gonna get lazy here and stop writing all of those additions, right? This was just the sum of f of x sub I times delta x, as n goes to infinity, right? I goes from 1 to n. So what I really have here is my integral definition. So this is the integral of f of x dx, and I'm multiplying the constant on after I do the integral process. And that's exactly what we have on the right hand side here. So here is a property of integrals that says that if I have a constant times a function, I can pull the constant out, then integrate the function and multiply the constant at the end of the process. Another property that we introduce in a section like this is that if I have the integral of a sum or a difference really, and I'm going to give myself a little extra room to write here, have the integral of a sum or a difference that's equal to the sum of the integrals. The sum or the difference of the integrals. I won't bother to go through a quick sketch of a derivation here, but you can see in essence I'm summing up a bunch of things added. So I can regroup terms, the associative property of addition. So when I write out all of these summations, my Riemann sums, I'm just going to regroup terms, and I'm going to end up adding each of the separate integrals apart. Now this could be very convenient for us in some future situations where the sum of f plus g could be a little more challenging or difficult to evaluate, and it would be kind of, I want to call it a shortcut, right, but a little bit more of an efficient process to separate each of those integral terms. We did this with derivatives as well, right? If I was differentiating like e to the x plus sine x, I would differentiate each of those terms separately, right? So could have an efficient way in order to accomplish this as well. Now the one thing that we're not going to see, so I'm going to write here not properties of integrals. So what is not a property is that the integral of f times g is the integral of f times the integral of g. That is not true. And if we think about with products when we did derivatives, we had a special product rule. So a little bit later in the chapter, we're going to look at like how do we do integrals of products. We're going to have some techniques that we use. So I'm going to say these two things are not equal to each other. That is not a property. And then the integral of like f over g is not equal to the integral of f over the integral of g. So just like we have a special quotient rule for derivatives, we're going to have a special technique that we evaluate integrals of quotients. All right, couple other properties to look at, and then we'll do some examples. Another property would be that if we have the integral of f of x dx from a to b, that's going to be equal to the opposite of the integral from b to a. And the concept here visually is if I'm integrating a function from a to b, what we had done in our definition, we had said delta x is equal to b minus a over n. And what we're doing visually is we're basically starting at a, going to b. So we're doing like final minus initial. That's always going to be a positive measurement. If I'm integrating from b to a, then I'm going backwards. So let me pick blue here. So if I'm going from b to a, my final is a, my initial is b. So I would have in that case a minus b over n, and that is going to be a negative value. That's a negative number, right? So what happens in that case is my delta x in my integral here becomes a negative value. So if I integrate backwards on my number line, I'm getting an integral that's negative. So one property of integration here is that if I switch the limits of integration, it changes the sign of my integral. Another property of integrals, which is really interesting that you see this written, but it is always written in a calculus book, is if I integrate from a to a, that is always going to be 0. And again, if we're interpreting as area, if I start at a and I end at a, I have no area there, right? So in order to find area, I got to go from a to some number bigger or smaller than a. So if I'm going from a to a, there's always 0 area under that curve. Now the last property that we'll look at for now is the idea that I can like split the integral up. In other words, I'm going to write it and then draw it. So if I have the integral from a to b of some function f of x dx, I can write this the integral from a to c plus the integral from c to b. And I'm getting sloppy and lazy here and leaving off the dx's. Now visually what this means is if I'm integrating some function from a to b, there could be some number c somewhere in the middle. Doesn't have to be somewhere in the interval. Doesn't have to be in the middle. Could be anywhere at any point in time. So my integral from a to c, I'm calculating here. And then the integral from c to b, I'm calculating that area. So of course the integral from a to c plus the integral from c to b is going to equal all the area under the curve. So the last property we'll look at in this section is the integral from a to b will equal the integral from a to c plus the integral from c to b, of course c being somewhere between a to b in our interval of our function. Alright, so let's start to take a look at a couple examples here where we apply all of the things we have just discussed. So in this first example, I want to evaluate the Riemann sum for f of x equals cosine of x from 0 to pi with n equals 6. Taking the sample points to be the left endpoints. Now remember, the Riemann sum is in essence all of the approximating rectangles, calculating the area under the curve. And I loosely use the term area because we could have negative area now that we've discussed more general conversations of f of x's, right? So in this case, the n equals 6 subdivisions is representing, how many rectangles that we would be using in this case. So I'm such a visual learner. I have to sketch the graph of cosine so that I can see what it is that I'm dealing with here. So cosine from 0 to pi looks something like this here. And if I was sketching this graph a little more precisely, I think what I'm going to see here, due to the symmetry of this periodic function, is I should get 0 as the value of the integral if I was doing it as a precise measurement. But because we're using n equals 6 rectangles, we may not get exactly 0 because we might have some overestimate or underestimate depending on what these rectangles look like, and we'll see that in a minute. We should get something kind of close to 0, I would think. So my Riemann sum being, if I write it out, right, I'm looking at the function times the width, and again the f of x represents the height of the rectangle, the delta x represents the width, and I'm going from 1 to 6. Now I'm going to go ahead and calculate my delta x, and so for this problem we have our b as pi, our a as 0, and we have 6 rectangles that we want to use, so our delta x is pi over 6. Now, if I start with left endpoints, right, I'm starting at 0, and then I'm going to go 1 pi over 6 away, so that's going to take me here. Then I'm going to move another pi over 6, that's going to take me to 2 pi over 6, which is really pi over 3. And then I'll move another pi over 6, so I got 1 pi over 6, 2 pi over 6, 3 pi over 6 is really pi over 2, right? And then I got 4 pi over 6, 5 pi over 6, and then of course 6 pi over 6 is pi. So let's see, 4 pi over 6 is really, this was 2 pi over 3, and then this was 5 pi over 6, and then we had our 6 pi over 6. So if I'm using left hand endpoints, right, I'm starting at 0. So my Riemann sum is going to be, so I'm going to go ahead and factor my delta x out, right? Like we've seen up to this point in the prior video, delta x is a common factor of pi over 6. So I'm going to go ahead and take out the pi over 6. So I'm looking at f at 0, f at pi over 6, f at pi over 3, plus f at pi over 2, plus f at 2 pi over 3, and then f at 5 pi over 6. So there's my n equals 6 rectangles using left endpoints for each of those rectangles. Now I'm going to come back, go ahead and draw these rectangles. So this first rectangle, right, goes from 0 to pi over 6, and I'm using the left endpoint. I'm going to come up to the function and draw out. My second interval is from pi over 6 to pi over 3. I'm going to come up the left hand side, shoot out, and draw that rectangle. And then from pi over 3 to pi over 2, on the left hand side, I'm going to come up, hit the function, come down. And then the next subinterval is from pi over 2 to 2 pi over 3. If I use the left endpoint, I'm actually at the x-intercept, so I really have no height to my rectangle. Then the next interval is 2 pi over 3 to 5 pi over 6, using the left endpoint, come down to my function. draw my rectangle, and then the last one at 5 pi over 6, hit my function, come out. So there's my 6 approximating rectangles. Now if I'm just looking geometrically for a moment there, and let's say I come in and shade, if I look at this first rectangle, the second rectangle, the third rectangle, the fourth rectangle had no height at all. Then I have my fifth rectangle and my sixth rectangle. So I don't think I'm going to get exactly 0 when I add all of these together, because I have 3 rectangles that are above the x-axis, positive area, and then 2 rectangles below the x-axis, which would be negative area. So I'll get close to 0. I won't get exactly 0, since this is an estimation, right, of the area under the curve. So I'm going to go ahead and scribble this out a little bit more and write out the details. So my function is cosine of x. Remember, that is the function that we are using to evaluate the Riemann sum. So I'm going to have cosine of 0 plus cosine of pi over 6 plus cosine of pi over 3, and so on and so forth. And then I got cosine of 2 pi over 3 and cosine of 5 pi over 6. Alright, I paused the video for a second so you didn't have to watch me calculate all of this. So cosine of 0 is 1, cosine of pi over 6 is root 3 over 2, right? Cosine of pi over 3 is 1/2, cosine of pi over 2 is 0, cosine of 2 pi over 3 is negative 1/2, and cosine of 5 pi over 6 is negative root 3 over 2. So you can see that I'm going to get root 3 over 2, negative root 3 over 2 cancel, half and minus half cancel, and I'm getting pi over 6 times 1, which is pi over 6. Now, if a problem like this is asking for an exact value, right, here's my exact value. If it's asking for a decimal approximation, that is about 0.524 rounded to 3 decimal places. Alright, so I just want to point something out to you here. The problem that I picked here was I want to call it a quote-unquote pretty problem. Well, all math problems are pretty, right? But this one worked out really nice in the sense that my delta x was pi over 6. And when I'm dealing with trig functions, right, that gave me multiples of 30-degree angles. So all of these trig function values here, cosine of 0, cosine pi over 6, these were all exact values. I could look those up on the unit circle. You know, you might have a homework problem in a section like this where the delta x doesn't turn out to be this beautiful pi over 6. Maybe it's like pi over 5. So, right, so if it's pi over 5, then I'm plugging numbers into this cosine function that I can't look up on the unit circle. So a lot of times in a homework problem like this, they will say, you know, give a decimal approximation. So we were able to find the exact value and then convert to a decimal. So if this was like cosine of pi over 5, right, you would be taking out your calculator and finding the decimal value for cosine of pi over 5, cosine of, you know, pi over 7, or whatever the case may be. And obviously when you're using your calculator to crunch those numbers, you want to make sure you're in radian mode so that you're getting the proper decimal value. Alright, in this next example, let's say we have the graph of a function g of x that's provided for us. And we want to estimate the integral from -2 to 4 of g of x dx with n equals 6 using midpoints. Now, just like we did in the prior video for 5.1, we were using rectangles, right, on graphs to estimate, you know, area under the curve. In this section, again, we took a more general approach and we defined the integral. And we never wrote the integral symbol in the prior video. So what we're really doing here, right, we're finding the quote-unquote area under the curve, remembering that area could be positive or negative here. And so I'm going to basically draw 6 rectangles on this function from -2 to 4. So using the 6 rectangles, I have to use midpoints. So first of all, just like I did in the prior example, I'm going to find my delta x. So my delta x is b minus a over n. So my b is 4. My a is -2, and we want 6. So that turns out to be 6 over 6, which is 1. So my delta x is 1. Now I'm beginning at -2 on my graph. So let's see. Looks like if I look at this piece here, right, looks like every 2 units is a unit of 1. So here's -1, here's -2. So I have a delta x of 1. So my starting at negative 2, my delta x of 1 takes me from minus 2 to minus 1, and I'm using the midpoint here to create the height of the function, the height of the rectangle, I should say. Right? So here's my first rectangle here. Now I'm going to come back and erase that middle line because that looks a little confusing. Right? So there's my first rectangle, right? My first subdivision. So I'm going to go ahead and write this out step at a time. Right? So I'm going to say that that first rectangle has a. So first of all, I have my delta x that I'm going to factor out. Right? So I'm using my Riemann sum. So let me actually step back one more time, and I'm going to say the integral from minus 2 to 4 g of x dx. This is going to be the sum of all of the f of x sub i's times delta x, and we're going from 1 to 6. So I'm going to go ahead and factor my delta x out as I write up all of these rectangles. So my delta x is 1. It's redundant for me to write the 1 out there, but I'm going to do it anyway. So there's my delta x, and then I'm going to say f at, so we said midpoints, right? So here's my first midpoint. What was that? Negative 3/2 was that first midpoint. And then my next rectangle is going to be here, and that midpoint is negative 1/2. So I'm going to come down to the function, hit my function here, draw that rectangle there. Alright, so that is going to be f at negative 1/2. And then I'm going to add my next subinterval. So my next subinterval goes from 0 to 1. Remember, my delta x is 1. And then I'm going to use the midpoint at 1/2, go up to the function, and that creates the height of that rectangle. And then my next, sorry, let me back up. That was f at 1/2. I'm getting ahead of myself because this is so exciting. Alright, so my next subinterval, delta x of 1, I go from 1 to 2, and again I'm using the midpoint there. So I'm starting at my midpoint of 3/2, and I'm going up to the function, hitting the function, that creates my rectangle. Excuse me. So that was f at 3/2 that we just drew. And then my next subinterval goes from 2 to 3. I'm going to use the midpoint there, and if you look at that, right, the midpoint f at 5/2, that's 0. So I actually have no rectangle, no height to that rectangle there. So f at 5/2 is going to be 0 when I write that down in a moment. And then finally, last but not least, as I go from 3 to 4, I'm going to use the midpoint there of 7/2. I'm going to come down, hit my function, and that creates that rectangle. So I have my f of 7/2 completes the 6 rectangles that we have there. So this is going to be, so let's come back then. So f at negative 3/2 was right here. What is that y value? So let's see, this was negative 1/2, this is negative 1. So that y value is negative 1. And then plus, so then now f at negative 1/2, so here's negative 1/2, and I come down to f, and that also is a y value of negative 1. Then we're doing f at 1/2, and that's a y value of 1. And then we're doing f at 3/2, and that's another y value of 1, the height of that rectangle. And then we said that f at 5/2 was the y value of 0. It's redundant to write it, but I'm going to go ahead and write it just for our conversation. And then last but not least, the f at 7/2 looks like that's negative 1/2 as the y value there. So adding all of that up, we get negative 1/2. So we could just kind of, I'm going to write a summary. I'm going to say negative 2 to 4. The integral of negative 2 to 4 of g of x dx is approximately negative 1/2, right? With our n equals 6 subdivisions and midpoints as the sample points. All right, in this next example, let's suppose we have a table of values for a function p of t that we've obtained from an experiment. We're going to use the values to estimate the integral from 3 to 9 of p of t dt using n equals 3 subintervals. And we're going to do this 3 times, left endpoints, right endpoints, and midpoints. I'm going to start to move a little bit quicker here. Please feel free to pause and rewind the video if you need to. All right. So we had done a problem really similar to this in the prior video in 5.1, but we had wrapped an application around it, and we had a table of values that were velocities. And so we were, using a Riemann sum to evaluate distances. We're not really given any context about what these values are measuring, but we have introduced the idea of the integral into this section. So we're basically revisiting a couple problems that we already did in 5.1, but we're framing it in terms of the integral here. All right. So the first thing I'm going to do is find my delta x, and I can't really call it a delta x in this case because my independent variable is t, so this is really a delta t. The delta t is b minus a over n. So my delta t in this case, my upper limit is 9, my lower limit is 3, and I'm dividing by 3. So that's what 6 divided by 3 is 2. So if my delta t is 2, I'm starting at 3, I'm going out to 5, and then from 5 to 7, and then from 7 to 9. So my delta t is 2, so again I'm going to write out that the integral from 3 to 9 of p of t dt is going to be approximately the Riemann sum of my f of, I'm going to call it t, and actually this is the letter p in this case. So we have p of t sub I times delta t. As I goes from 1 to, we have 3 subintervals. So in this case, if I'm using left endpoints, I'm going to pick a different color here. So I'm using a left endpoint for this first rectangle. My left endpoint is here at t equals 3. So again, I'm going to get efficient, and I'm going to factor out my delta x of 2. And I'm going to evaluate each of my values. So I'm going to have p at 3, and again I'm going to do a little bit different than the last time. Just go ahead and plug that number in. That's negative 3.4. And then for my next rectangle, I'm looking at t equals 5. So I have p at 5, and based on that table, that's negative 0.6. And then my last rectangle, I have t equals 7 to 9, right? So I have p at 7, and that is equal to 0.9. Taking out my calculator and crunching all of that, I get negative 6.2. So I'm going to write over here that my left endpoint with 3 subdivisions is equal to negative 6.2. So go ahead and pause the video real quick if you're scribbling down notes. I'm going to erase what I have here and start over again doing the right endpoints. Alright, so I'm cheating a little bit. I'm going to be a little efficient, and because I have erasable marker, I only erased the things that I'm not going to use for this next step. So notice that I left the integral from 3 to 9 here. We still are going to have the same delta t, of course, because we're only doing n equals 3 subintervals for each of these problems. So what I had here in blue, right, I'm starting at 3, going to 5 because my delta t is 2, starting at 5 and then going to 7, and then starting at 7 and going to 9. So those are my 3 subintervals. So if I'm doing right endpoints, I'm going to use the right value of each of those endpoints. So for that first rectangle, t equals 5 is my right endpoint. So I'm going to be finding p at 5, and then t equals 7 is the right endpoint of that next subinterval, so I'm going to be finding p at 7. And then for my third and final rectangle, t equals 9 is the right endpoint, so I'm going to have p of 9. So looking at that table, p of 5 is negative 0.6, p of 7 is 0.9, and then p of 9 is 1.8. and plug in all that, and my calculator gives me 4.2. So I'm going to come over here and say r sub 3 is 4.2. Alright, so again, I came back and erased what I didn't need. I'm going to do the midpoints last. So again, delta t is 2. So I'm starting at t equals 3, and I'm going to t equals 5, t equals 5 to t equals 7, t equals 7 to t equals 9. Now I'm using the midpoint of each of those intervals. So for that first subinterval, t equals 4 is my midpoint. So I'm going to have p at 4. Then my next subinterval is t equals 6. So I'm going to be evaluating p at 6. And then that last subinterval midpoint is t equals 8. So I'm going to be evaluating p at 8. So looking at the table, finding each of those values, p at 4 is negative 2.1, p at 6 is 0.3, and p at 8 is 1.4. And I'm getting negative 0.8 out of my calculator there, so my midpoint with 3 subdivision is negative 0.8. In this next example, we're going to focus on the interpretation of the integral being area under the curve. And again, when I say area under the curve, or the under meaning between the function and the x-axis, where we could have signed area here, right? So I'm going to switch to my blue marker and think about this region here and this region here in blue, right? Those are going to be positive areas because the function's above the x-axis, right, like we talked about before. And if I look at this area here, right, that is going to be a negative area because that is that function is below the curve. So I'm going to use the property of integrals here, and I am going to, let me erase this stuff real quick. So with my property of integrals, what I'm going to do here is, because I'm integrating from 0 to 14, I have basically 3 different functions that I'm integrating. I'm going to think of this as a piecewise function. So if I look at the scaling here, it looks like I go 2, 4, 6, 8, 10, 12, and 14. So the object here is not to actually find equations of each of those pieces of graph. It's to interpret as area. Right? So remember, we had that formula for integrals that said we could go like from a to b of f of x, and we could write that as the integral from a to c plus the integral from c to b. So we could split up our integration at any point within the interval from a to b, and I'm going to do that in this case. So in other words, I'm going to integrate from 0 to 4, and I'm going to find that area under the first piece of that curve. So I'm going to say the integral from 0 to 14 of g of x dx is going to equal, I'm going to integrate from 0 to 4 and find that area, and then I'm going to integrate from 4 to 12 and find the area of that semicircle. So I'm going to go 4 to 12, and then I'm going to integrate that last piece, which would be from 12 to 14. Again, the only way we can really find the exact value of this integral is that I'm going to be able to use geometry. So we haven't learned any of our shortcuts of integration yet. That will be our next video. But knowing conceptually the integral calculates the signed area, having line segments in a semicircle makes this straightforward, right? Something that I can actually measure. So if I look at that first area from 0 to 4, let me pick a different color. So I'm going from 0 to 4. I'm finding the area of a rectangle here. So I'm going to have 1/2 base times height for that first piece. Now what's the base of that triangle? It's 4, and the height of that triangle goes all the way up to 8. Alright, now the next piece of area is a semicircle. So I know that, pi r squared is the area of a circle, so I want 1/2 pi r squared. Now keep in mind, all of this area down here is negative, right? So I'm going to have a negative 1/2 pi, and then r squared. So what's my radius there? So I'm going from 8 to 12. That's a radius of 4 pi r squared. And then that last piece, again, I have a triangle, then do 1/2 base times height. So the base goes from 12 to 14, so the base is 2, and then the height is 2 as well. And again, just to point out to you, the first triangle I left as positive 1/2 base times height because it's above the x-axis, as well as that last triangle I left as positive because it's above the x-axis. So crunching all of this out, I get 1/2 times 4 is 2, times 8 is 16. I'm going to get minus, let's see, 4 squared is 16, half of that is 8. And then let's see, half of 2 is 1, times 2 is 2. So I got what 16 plus 2 is 18, minus 8 pi would be the value of the integral based on the given graph. So another problem we might see in a section like this is very similar to what we just did in the last problem, except in this problem they're not sketching the graph for us. So we're going to evaluate the integral from -2 to 5 of the function 3 minus x, and I'm missing a dx there, by interpreting it in terms of area. So I'm going to sketch the graph of my function. So what does y equals 3 minus x look like? Alright, so let's see, that's the graph of negative x plus 3. So I'm going to have negative x, line is sloping down, negative x plus 3, shifted up 3 units. And let's see, my x-intercept there is going to be 3 as well. So I'm going from -2 out to 5 are my limits of integration. So again, in this problem, in this section, these problems where we're interpreting as area, we're going to have some geometry that we can use. So in this case, we basically have, 2 triangles. So just like in that last problem, I'm going to go from -2 to 3, and I'm going to look at the area of that triangle. And then I'm going to go from 3 to 5, and I'm going to look at the area of that triangle. So again, I'm going to write this out conceptually, that our integral from -2 to 5 of the function 3 minus x, we're going to go from -2 to my x-intercept here of 3. And we're going to calculate the area of that triangle, and then we're going to go from 3 to 5 and calculate the area of that triangle. So that first triangle from -2 to 3, so if I go from -2 to 3, that is a base of 5. And then my height of that triangle is over here at -2. So what is the y value when x is -2? That's going to be 3 minus -2, 3 plus 2, which is 5. And then again, that next triangle is below the x-axis, so that's going to be a negative quantity. So I have base there, so I'm going from 3 to 5 as a base of 2. And then what's the height? So again, the height is going to be the y value at x equals 5. So my function is going to be 3 minus 5, a height of -2. Now, I'm noticing something I want to be careful of here. Because I'm actually plugging into the function, the y is coming out as -2. So I actually don't need the negative that I wrote in front of that 1/2. The reason we did that on the prior problem is I was doing pi r squared, the area of a circle. So again, I'm plugging x equals 5 into my equation, and it is producing a negative y for me. So let's see, what are we going to get? We're going to get 25 halves, and this is going to be -1. So that's 25 halves minus 2 halves, and that's going to give me 23 halves as the value of the integral -2 to 5, 3 minus x dx. Let's take a look at one last example, which combines all of these ideas that we've been discussing in this video. So in this example, we have an integral defined function, and then the function is defined as cap f equals the integral of little f of t from 8 to x. So we are being asked to place the following 3 values in numerical order from smallest to largest. We're going to find cap f at 0, cap f at 8, and cap f at 16, and I actually want that to be cap f at 20. And I wrote out there at the end of the graph, or let's suppose that ends at 20 there. All right, so what we're going to do in this case, what I want to do is kind of take a look at each of these values separately, right, and then let's put them in numerical order. So if I'm finding cap f at 0, let's think about what that's representing. As an integral, we're going from 8 to 0 of f of t dt. Now, suppose I was going from 0 to 8. And if I'm going from 0 to 8, we're starting at 0 and going out to 8. The area under the curve there is going to be a positive measurement because it is above the x-axis. But in this case, we're going backwards, right? We're going from 8 down to 0 backwards, so that's going to give us a negative measurement of area. So I don't really know exactly what that number is without putting rectangles in there. You notice I don't even have a scale on the y-axis, so I couldn't even really estimate a true measurement here. But I know that's going to be some negative number. So I'm going to say, this is equal to some negative number. Okay, so whatever that value is, we know that it's a negative number. So now let's consider f at 8. So if we're looking at f at 8, then we're looking at the integral from 8 up to 8 f of t dt. And again, we know from prior conversation, the properties of integrals, that if I'm integrating from a to a, that's going to be 0. And again, if we're thinking of area under the curve, if we're going from x equals 8 to x equals 8, we haven't accumulated any area in that case. So the area that we're going to have there is 0 for the value of f at 8. Now if we look at the last value, let's say f at 20. Now, let's think about this collectively here. If I'm going from the integral of 8 to 20, let me change to a different color, blue. So I'm starting at 8, and I'm going out to 20. So that is going in the correct direction on my domain. X is going from a small to a large chronologically. So the area under the curve here is going to be a negative number as well. So this value, the integral, cap f at 20, right, that's also going to be a negative number. So now that we looked at each of these values individually, we're being asked to place them in numerical order from smallest to largest. So when we're looking at these values of these three integrals, 0 is going to be the largest value because the other two are negative. Right? If we think about plotting these numbers on a number line, here's the number 0, here's positive numbers out here, right? And then I have negative numbers out here. So 0 will be my largest, and then which one would be my smallest number? So when we're thinking about area under the curve here, if we think visually, the integral from 8 to 0 is a smaller amount of area than the integral from 8 to 20. Right? So in comparison of those two negative measures, this integral here, pick the wrong color, this integral here from 8 to 0 is the smaller sized area. So it's the smaller negative number. So it's going to go here. That would be f at 0. And then the larger sized area is the bigger negative number. So it is going to be more negative and smaller. So putting these in chronological order, we're going to have f at 20 being our smallest value, our most negative. We're going to have f at 0 and then f at 8. Alright, so that really covers everything in this video. I want to do a quick summary. We discussed a lot of stuff here. So we started off this section defining the Riemann sum, reminding ourselves of the Riemann sum really from the prior video. And then that allowed us to introduce the integral symbol. So we defined the integral from a to b as the limit of the Riemann sums. We said as long as f is defined, right, and where that limit exists, and we talked about a vertical asymptote would be a possible place where the limit doesn't exist. We're not going to focus on that right now, but we'll take a look at that later. So we were able to formally define an integral. We then began discussing some properties of integrals, the first one being the fact that we can have signed area, as we've seen in all of our examples. The next property being that we can take a constant out of the integration process and multiply it back on at the end. We then discussed that the integral of a sum is the sum of the integrals, which is true for a difference as well. We talked about how we don't have properties of integrals that deal with products or quotients. That'll be something we discuss in a future video. Then we discussed the concept that we just used in that last example, which is when I switch the limits of integration, it gives me the negative of the integral. And we talked about moving in a positive direction as x increases, as a negative direction as x decreases. The next property we looked at is when we don't move on our x-axis. When we move from A to A, the area under the curve would be 0. We just used that in that last example as well. And then the last property we looked at was what we also used in that last two examples, where I can, in essence, split up my limits of integration at any point between my interval a to b. So if I'm integrating from a to b, I can split it up at some number c that lies in between a and b. So after the discussions of all of those properties and where those ideas come from, we took a look at quite a few examples of evaluating Riemann sums. We evaluated them numerically when we had a table of values. We evaluated them graphically, given a graph of a function, and we evaluated them given an equation of a function, as long as we could draw the graph and interpret that as area. So that is everything I wanted to discuss in this video with you. Hope you had as much fun as me, and I look forward to seeing you guys in the next video.